Welcome everyone to the official YouTube channel of REOS. We'll be using this channel to post regular tutorial videos and full recording of our technical webinars. Today in this introductory video, we are going to walk you all through the modeling and simulation of the building structure from start to finish. But before we start, let me give you a quick overview of what REOS actually is. REOS is an advanced graphical user interface and external orchestrator designed specifically for OpenSees-based structural simulations. It features rich pre- and post-processing capabilities, allowing you to build structure of any scale highly efficiently and then interpret and visualize the results exactly the way you need them. So let's jump right in and get started with today's discussion. So this is the interface you can see. It's a graphical user interface where you can model the structure in a story to story based way. We'll shortly show you how the modeling is carried out. But before that, let me give you a description of the model we are going to simulate today. Okay, let's first build the structure. Then after that, we'll show you the configuration. So we are going to specify the number of stories. Let us assume a five-story model, sorry, six-story model. And here you see you can specify the story height. For this demonstration, I'm just going to assume the default 3-meter story to story height. Then let us define the grid space in both the directions. So I'm defining 4 grid space in both the directions. Again, uh, here you can specify whatever grid space you want, but I'm going to keep them as it is. So this is how finally your grid setting is, and now you can draw your members nodes wherever you want. So we'll start from the base, then we'll move up floor by floor. So here you define the plan where you want to visualize the plan view. We'll start from the base story and then press the plan button. Then you can click on this add node. Now you can draw your nodes here. Then we'll move to the next floor and we'll do the same thing here, adding the nodes to uh, the joints. Then you can connect the nodes by drawing the members. Now you can active the 3D view and see how your first floor looks like. The beams are drawn in both the directions. And now either you can continue drawing nodes and members in each floor, or otherwise you can extrude the whatever you have done in the first floor to the subsequent floors, and it will save a lot of time. And this is what we are going to do now using this extrude option. So here we can see above the first floor we have total 5 floors, so we'll make this into 5, and here you decide from which floor you want to copy the properties, and these are the things by default you can keep as it is, and then press OK. And now you can see whatever we have drawn in the first floor, the same thing has been copied to the all other floors. Similarly, now you can active one of the elevation view and draw the members in one of the grid line, and copy the same thing to the other grid lines. If the structure is symmetric, it is useful. If you have like unsymmetric properties, then you can do it manually. So we can connect the nodes here, and you can see in 3D view whatever we have drawn so far. Again, you can go to this edit option, then click on replicate, and now you can see the properties are going to be replicated in y direction. Here you see the axis system. We are going to copy the properties from this grid to the other grids, which are basically moving forward in y direction. So we have to click on this y grid, and this grid is actually grid A, that you can see here. Then you can mention which direction to move with the updated properties. Since we are going to move in the y direction, so you will have to mention the offset for y, which was actually 3000. And if you want at any radial orientation, then you can also mention the angle, but in this demonstration we are not going to use them. So click the OK button, and now you see the properties from grid A has been copied to the grid B. In the same way, you can copy to all other grids. Now you can click on B and again 3000, then C 3000, and then D 3000. You can also do like selecting here A, then instead of 3000, you can mention like 6000, 9000, 12,000. That is also possible. So your model is like uh, prepared with beams, columns, etc. But please note that we have not yet assigned any member or material properties. This is just a base model with the geometry defined. Not geometry also. This is like wireframe model where only the line diagrams are drawn. Now we have to assign materials, then we have to assign the member element properties, all those things. Okay. Before moving to that, we can also actually increase or decrease the size of line width and nodes. So I think this will be appropriate then. Node size also we can reduce, although we need the nodes for subsequent process, so I'll let them as it is. Now we'll define the materials, then elements and other member properties, whatever we need one by one. First, let's start with the material properties. We can call from the OpenSees library. For this demonstration, now let me show you the model configuration we are deciding for this example. Okay, so actually I have prepared this already so that it becomes easy for this discussion. So this is how the analysis is going to be. First, we'll run the static analysis, then we'll run the pushover analysis. The pushover will start after the gravity analysis ends. Then also we'll run the nonlinear time history analysis. This is actually again going to be starting after gravity analysis, not after pushover, because both are actually the representation of earthquake loading. Either you can do pushover based analysis or you can do nonlinear time history analysis. We are going to discuss both the things. Okay. So in the modeling scheme, we have decided the beam members to be modeled as frame elements with concentric nonlinearity at the end of the members. And accordingly, the intermediate region between the plastic hinges will be modeled using elastic beam column element from OpenSees. And the plastic hinge regions are going to be modeled using the zero length element assigned with modified IMK material model. Column members are going to be modeled using beam with hinge element assigned with fiber sections at both the ends of each member. So for this purpose, we need to also define the material models, like for concrete, what material model we'll be using, for steel, what material model we'll be using. This structure is going to be RCC structure. So the concrete will be modeled using the concrete 02 material, and steel reinforcement is going to be modeled using steel 02 material. We are also going to assume that the floor diaphragms are rigid in plane, and it is going to be simulated using the equal degree of freedom command. Then for the loading purpose, just to make it easy, we are going to use two kind of loading. One is the live load at floor levels, and the other type is going to be the masonry infill load coming transferred to the beam members. Then the pushover analysis is going to be carried out in displacement control mode, and the nonlinear time history analysis is going to be carried out in transient mode. So for the transient analysis, we need to also define the Rayleigh damping parameters. And here actually I am not going to calculate the exact damping parameters. Just some assumed values we'll be using, and we'll see proceed with the simulation. The beam members will be assumed to have the cross section of 300 by 450 mm. Then column member will be having the cross section of 400 by 400 mm. And in the fiber section, we'll be using 8 rebars for the column members of 20 mm diameters. The material will have the grade of 30 MPa for concrete and 500 MPa for steel. So these are the basic information we need for carrying out the simulation. So let's start again. We are going to define concrete 02. We'll edit the properties later on. First, I am just creating a library of materials what we will need for this discussion. So we are going to use concrete 02 and steel 02 material. Then for the beam members, we need an elastic material. and also the modified IMK model. So now you can see whatever members materials we have selected, that all are stored in this left side panel. In a similar way, we can uh, first define everything. After that, we'll edit the properties from the left panel. So material are selected, then we can proceed with the elements. For this discussion, we need an elastic beam column element for beams, then zero length element for plastic hinge region of beams, and then beam with hinge element for column members. So again, you can see the elements whatever we have selected are stored in this panel. Then we need a fiber section for the plastic hinge length of column members. Here you see this is the fiber section for concrete, and we have also customized fiber section for steel. So we'll select this one, and now here either you can edit the properties here or you can edit later on. Okay, so we have to give some material properties here. So here you can see you have the option to provide separate properties for core and cover concrete, but just to make it easy, we are going to use the same properties for both core and cover concrete. But in real case, we'll be using the confined concrete model for the core region and unconfined for the cover region, and steel for reverse. Here you can define how many fibers you want in each direction. Let us make it 3 by 3 in both the direction, and now here you have to add the reverse cross section and coordinate in your member cross section. We have a 400 by 400 cross section, and we are assuming that the effective cover is going to be 40 mm, so your effective core region will be 320 by 320. So you have to provide the coordinate. Our origin is at the center of the cross section, so if you take a left bottom corner, then it is going to be minus 160 by minus 160, and the 20 mm dia cross section will be 3144.15, something like that. Then add. Similarly, you can add all the rivers. Minus 160. So the rebar layout is created. So in a structure, if you have multiple member cross sections and multiple rebar configuration, you can do the same thing for all the members. But in this case, we are going to assume the same configuration for all the members. That's why I've created only one layer. Then, so here we have created all the things we need. We can now define this transformation property. We need two transformation. One is for beam, another one is for column. Let me first define, after that we can edit accordingly however you want. Then we need another one. Here you can see the transformation command we have created stored here. Then we need this time series. Here we need three time series. One is for the gravity load application, another one for pushover load application, another one for ground motion time history load application. So we'll just define now. Later on we'll edit. Okay. So this is again stored here. Then we need load pattern. So here again we need three load pattern. One is for gravity load application, another one is for lateral load application, another one is for uh, earthquake ground motion load application. This is going to be second one. Sorry, this is sorry. Okay. So we have first, second, then we need another one, third one. So we have three patterns and three time series. Then we also need the mass application. Before mass, let us first define the load pattern, what kind of load we are going to apply. You just need to type the names like floor live load. This is not a OpenSees command. Just for making it easy during modeling, we have created this customized command. Then infill world load, and now we can go to. So based on our unit, actually we have used the unit of Newton mm in second. So your mass density is going to be 2.5 into 10 to the power minus 9. And this gravity acceleration is going to be 9810, and the application is going to be negative z. Here you see the load pattern we have created and how much of this load pattern you want to assign as a mass factor. So we are considering full load and for which degrees of freedom you want to assign the mass. So we are assuming that all the translational degrees of freedom will be assigned with seismic mass, and rotational degrees of freedom we are not going to consider for this. Then you need to also define the Rayleigh damping parameters. As I said, I'm just going to assume some values, although in real analysis you will be calculating the parameters based on your time period and uh, damping coefficient values. Then we need to define the rigid diaphragm constraint. We are using actually equal degree of freedom constraint. Just give some name, flow diaphragm, EQ degree freedom. So I think we have defined all the things we needed. Now we just need to edit them with appropriate parameters. So first let's start with the materials. Concrete. By default it is 30 and this is what we are going to use. This is the strain corresponding to the peak stress and this is the ultimate stress. Although this is a little bit complicated to decide, but it will not make big difference. So let us keep whatever is by default, and the ultimate strain I am going to use as 0.004, and we are going to ignore the tensile strength, and this is the tensile modulus. This is actually, it sometimes helps in convergence during analysis. If you keep high value here, sometimes it shows some convergence failure. Then in case of steel, the grade was 500. This is the strain hardening. We are going to use a very low strain hardening. Then this is actually how sharply your curve bends here. It represents this. If you want to see under cyclic loading how your steel will behave, you can go to this one and you can see this is how it is going to behave. So the disadvantage of this model is that it doesn't have any degradation. Uh, there is virtually no degradation in this model, irrespective of whatever strain value you are using as the maximum value. If you want to use this in real simulation, you have to wrap it up in a min max model. But for this, we are not going to use this min max model. Just as it is, whatever model is there, still 02, we are going to use it directly. So one more thing, instead of still 02, another better option is to use hysteretic model. There is another model named hysteretic model that can be used for either material modeling as well as for member modeling. So that steel 02 is like suitable for earthquake loading simulation, and there you can simulate all kind of degradation parameters also. So when you will be modeling in real, you can either decide to go for that hysteretic based model or steel 02 model wrapped up in a min max constraint. Then you can use it. Then this is the elastic material model. So we are going to use some high stiffness. So this material will be assigned to the degrees of freedom where we do not want the plastic behavior to occur. Like for example, if you want to simulate the nonlinear behavior only in the flexural behavior mode, then you can uh, disable the other mode or other degrees of freedom by assigning this elastic material. Then this is the IMK material model we'll be using for simulating the nonlinear behavior, and it will be used in the degrees of freedom where you want to simulate the flexural nonlinearity. Okay, so the default parameters, actually these values are calibrated for beam members of 300 by 400, and whatever you can see here, that is reasonably good for a 300 by 400 member, although in this discussion we are using 300 by 450, so it doesn't matter. For this discussion we can keep it, but for actual simulation you can use the values whatever is appropriate for the member you are using. I'm just going to change this little. So the materials are corrected, then we can edit this. So this is the beam member. As I said, we are going to use the cross section of 300 by 450, and this is the concrete Young modulus definition. According to Indian code, I am defining 5000 root FCK. So here that coefficient we have to assign, and the rest software will calculate. Then you click on this update and the parameters will be calculated. Then zero length element for beam members. Here you see the thing I was explaining. Out of 6 degrees of freedom, only this Rx and Ry is going to be non-linear to replicate the flexural behavior, and all other degrees of freedom will be considered as linear elastic. There will be no damage simulated in those degrees of freedom. So this is a pure flexural behavior simulation we are going to concentrate. So you have to select here which material to be assigned here. Now, if you see, our elastic material is having the ID of 3 and IMK is ID 4. Okay, so you click 3 here and here and 4 for this. So this basically flexural response in X as well as in Y direction. If you want to define different material like two IMK material for X and Y direction, so accordingly you can decide the IDs here. Okay, but for this discussion, since we have a square cross section and the reinforcement layout is also symmetric, so in both the case, sorry, in case of beam, we are talking about, uh, yeah, it will be different, but no, it is not going to be different because all the beams either in X and Y direction are having the same configuration, so we'll have the same properties. Sorry, I made little mistake here. This is not with respect to the global direction. So here you see Rx and Ry is the local coordinate of the member. Okay. So if you are providing the member along the X direction, so either Rx or Ry will govern. Okay. So we are basically defining two means same properties in both the direction, although one will govern. Either you can decide to use the appropriate values here for each direction. But since only the major axis will govern, the minor axis will have less influence, so it doesn't matter here. Okay. Then we are done with elements and materials. Now the section here, this is column, so we have decided to have the member cross section of 400 by 400 and cover thickness of 40 mm, and the rest already we have defined earlier. Just click OK. So then we are now okay. Now geometric transformation in case of columns. Actually, this discussion will need a little longer, so I am going to actually skip this part. We'll have technical webinar soon in the next like 24th of this month. There we'll have full discussion of this one. For this demonstration, I'm skipping this, but just to let you know, for column, we are going to keep x vector as 1, then the rest as 0. And in case of beams, we are going to keep this 0 and this 1. Then we have the pattern. This is going to be used for, here you see the pattern 1 with first time series we have created here. This is going to be used for gravity load application. Then we are going to use the first letters, define all the time series properly. The second time series is for the lateral load application. We are going to use this path, and here we'll select the time history for pushover based loading. Here we have stored the time series. Let me show you. Actually, this is again a linear time series I have defined from 0 to 1 in 1000 steps. Okay, here let's make it uh, 10,000 seconds total. So we have total 1000 steps. If I want to make it a 10,000 second duration, so I have to multiply it by 10. So 10,000 means roughly 166 minutes, which is roughly 2.7 hours. Means we are applying the loading gradually. Okay, it's fine. Then we can similarly define the other time series for the ground motion application. Again, we have another. Actually, we are going to use the 1964 Northridge earthquake, I guess. Let me also show you the actual time history for that. This is the actual time history downloaded from the peer ground motion database. Here you see, sorry, the earthquake occurred in the year 1994 in the Northridge region, and it has a duration of 1999 seconds. Sorry, total 1999 points, and the time step of 0.01. So the duration is 19.98 seconds. Okay, so instead of using this as it is, I have just reframe the values in a single column. Okay, and as you have seen, the duration was 19.99 seconds, but we have total data points of 1999. So to make it to 1900, sorry, 19.99 seconds, the duration time step is 0.01. And now you can select the appropriate time series here for the lateral load application. And here, in case of ground motion application, you have to select either uniform excitation or multi-support multi-support excitation. So in case of building structure, generally multi-support excitations are not governing actually, because you have a very less plan length. So within, let's say, if you have 50-meter plan length, also multi-support excitation doesn't uh, occur actually in this. If you have a like long span bridge, like the piers are at several hundred meters or maybe like 1 kilometer far from uh, the next pier, in that case you can consider multi-support excitation. So we are going to use the third time series for that, and we'll use the x direction for the ground motion application. Then press OK. Now let's define the rigid diaphragm. We have to actually select the master and slab nodes for each flow separately. So we'll start from the first story. So before doing this one, you have to select the degrees of freedom here. So we are going to constrain the lateral translation along x, translation along y, and rotation about z. Pick master node. I'm going to use the central node as the control node or master node. Here you can see whatever node you click, that will be displayed here. Then pick slave nodes. Now you have to select the nodes one by one. and then here you select the story, corresponding story, and assign. Now you can see it has shown, means to confirm that the diaphragm has been assigned. Similarly, you can go to next floor and select the master node again, and now you see the number is changed here. Then again pick slave nodes, and then pick storage 2 and assign. Similarly, do it for the other stores. There is one extra grid level created at 7th story, although we do not need because our demonstration model is actually having 6 stories. So then click OK, and now you can see the diaphragm is assigned to all the floor levels. Now, whatever material element and member properties we have created will be assigned to the members. So we have just hidden the diaphragm constraint, and now you have two options. Either you can select each member individually and assign the geometric and material configuration, or you can select all the members together and assign the properties if they are having the same properties. Now, for this example, we are assuming that all the beam members will have the same properties and all the column members will have the same properties. But I'll show both the options. First, we'll select a single member, and then we'll proceed with all members together. Okay. So, for individual member assignment, you can go to this Let me collapse this all the panels except this one. We need this. So you can click on any member and the same is highlighted here so that you can understand in which member you are assigning the properties. Okay, you can double click on that and this panel will come out. In that you can decide whether you want to go for the like frame element modeling or the fiber element modeling. Currently REOS has the capabilities to simulate the frame and fiber based modeling. The shell based modeling is not yet implemented. It is actually for the future version of the software. Now for beams we are going to use the frame based modeling. The intermediate region is, as I discussed earlier, using the uh, elastic beam column element and the plastic hinge region using the zero length. Now, as you know, if you want to use the zero length element, you have to create additional nodes. That's why you have to click on this. And if you uh, could observe here, if I check this box, this is actually unlocked. So here you select the whatever nonlinear material model you have created earlier. Okay. Now here you have to select the intermediate region property, which is going to be the elastic beam column. I have to check the ID of that. This is here. The elastic beam column is having the ID 1 and the beam width hinge, sorry, this is for column, and the zero length element for beam is having 2. So you go to this option again and check this. This is 1 by default, this is correct, and here I have to select 2. Actually we have only one modified IMK model, so only one is by default appearing. If you have multiple, then you have to select out of them. And now here geometric transformation tag, in case of beam it was the second one. And if you want end releases, you can check these boxes here. Now if you go to this rendered view, here you can see the cross section, means the whatever properties you have assigned is reflected here. Okay, similarly you can go to all other members wherever you want to assign, but this way it is little bit inefficient because you have to select each and every member separately. So instead of doing this one, you can select all the similar properties together and assign the member properties at the same time. So let me check this. And now what you can do is click on this select option and drag your mouse to select the So you can see all the members are selected. Now you can go to assign, then assign properties, and here you see currently selected member. So you can do another shortcut also. Instead of selecting here directly, you can go to assign properties and select all beams or all columns if you want to assign the properties to all the beams or all the columns. Okay, then go to assign, and here again the same panel which we have used earlier for individual member assignment. Enable the extra node, and here you have to select 2, and the transformation tag is going to be 2. Now you see the properties are assigned to all the beams. Similarly, you can do for the column members. You can go to one of the elevation view. Sorry, we will not use the elevation view. Better to use the 3D view. Then click on this select button and again drag the mouse. Then again go to assign and currently selected members. Go to assign. Here you select the fiber based modeling and beam width hinge. Since we have only one uh, ID created here, that's why if you have multiple IDs, then you have to select from the drop down. And here the transformation tag, we have decided the first one for column. Then click OK. Now if you see the rendered view, sorry, there is a little problem. Here it is showing the properties are assigned, but it is not. Let me close the module. Okay, actually we have done a mistake here. In case of beam width hinges, we have not defined the cross section. So that's why the cross section, although it is assigned, but here it is not visible. As you can see, this is a very minor value, so it is not visible actually. So we have to specify the cross section. Then the plastic hinge length, we'll assume half of the cross section depth, which is going to be 200 mm. And here you select the section. So section ID is one, and by default it is showing here. If you have multiple, then you have to again select from the drop down and update and click OK. So I think it is created correctly. Yeah. Now you can see. So I was little bit skeptical why it is happening. I was not actually getting. So it happens sometimes. Now you can again click on this, just uncheck this, and we are going to assign the support constraint. So first select all the support nodes and go to assign restraint and select fixed. Okay. Now you can see the fixed support conditions are created. Okay. So we are done with the geometry creation, and now we can go to assign load. So first we'll apply the floor live loads. So you can go to the first story, then click this one, select all the members, then go to next. So we are assuming that all the floors will have the same loading, including the roof level. Although in real, the roof level will have the different loading intensity. So you can see all the beams are selected. Now you can go to assign, then assign load, and here you decide the category of load. This is going to be floor live load. Then the pattern what we have created. The first one was for the gravity load, and the type of load you want to define here. We have to select, since this is going to be a distributed load acting on the beam member. So we have this option that we can utilize for. So again, you can select either of these two. Like if you have an existing load that you want to replace with a new load intensity, so you can click on this. But at present, since there is no load acting on the members, it doesn't matter whichever option you can decide. And here you decide the direction. It is going to be negative z, and the intensity at the start and end of the, because we have selected the trapezoidal load. And OpenSees actually simulates the load as uniformly distributed. Okay. So based on that, we have to select the same intensity at both the ends. And for this demonstration, we are going to use 8 Newton per mm as the load intensity. Then click OK. So you can see the uniformly distributed live loads are applied to all the beams. Now, in a similar way, we can also apply the other load types, which is the masonry infill load in this case. So before that, let me hide the applied load. Again, let's go back to first story. In this case, in for the infill frame loads, will not consider the roof level members because there will not be any partition wall on the roof level, although there will be parapet wall. But for this example, we are not going to uh, consider the parapet wall load. So we are selecting the members again. So we have selected all the beam members excluding that of the roof level. Now we can go to the assign load, then select here the infill wall load and the same pattern here because this is also the gravity load, and again we can select this trapezoidal option and you can choose either of these two options. Here considering a 300 mm thick wall, the intensity will be approximately 18 Newton per mm. Then hit OK. So again, you can go to view load option if you want. Select the infill wall, then show loads. Now you can see the loads are applied to the members. So so by now we have created the model, then we have assigned all the properties including material element, and we have also applied the loads. Now, okay, there are some load applications left out with respect to the pushover analysis and the ground motion. I think for ground motion we do not have to do anything because we have selected the uniform excitation. So during the analysis, software will automatically take care of it. Means the ground acceleration will be applied. We do not have to apply directly to the model. But in case of pushover, we have to apply the pushover load pattern to the structure directly uh, using the control node and specifying the intensity directly into the model. So before applying that, let me first explain few things regarding that. So let me open a notepad. So you might be knowing that the pushover load is usually applied with respect to the mode shape pattern. Generally, it is a nearly parabolic shape, and you specify that shape. Either it can be a parabolic shape or any other, depending on what is the shape of the mode or any shape which is relevant to your case. Now, in this example, we'll simplify it a little bit, like linear shape we can apply, because otherwise we have to calculate the ordinate of parabolic shape. Now, again, one more thing important is you cannot randomly decide this one. The shape will be decided based on the model analysis. Now, in this example, we are not going to carry out the model analysis. Uh, if model analysis is run, then we definitely have the mode shape known, and we can take the same mode shape and apply the load accordingly. But for this example, we'll assume a mode shape instead of running the model analysis first. So, so let's say this is our structure. We have a 6-story structure, and what we are going to do is we'll assume a linear mode shape, although it is not realistic because the actual structure will not have a linear mode shape in the fundamental mode. But for the sake of simplicity, we are just assuming this one. So this is the lateral displacement at top floor, then the story below that. So now let's say I want to apply a lateral displacement of 400 mm at the top story. So the we have total 6 floor. Let's start from the bottom. Let's say I want to apply 50 mm here. So I have to apply 100 here, 150 here, 200, then 250, 300. So this is the pattern I am going to decide for this structure. Now the thing is that when the structure goes into nonlinear zone, uh, based on the actual capacity or actual distribution, force distribution of your structure, because for example at some stage one of the member fails, so if you push that member, it will not take any load because it has already collapsed. So finally your shape at the end of the analysis may not be a linear shape, depending on how the structure actually behaves. So this linear shape will be true only till the linear elastic phase of the structure. Once the structure goes into inelastic zone, so it will behave based on the actual capacity of the structure. Okay, but at the beginning we are going to assign this load distribution pattern for the pushover analysis. So that load distribution will be applying through the control nodes or the master nodes, those we have decided during the rigid diaphragm application. Okay, so we'll start from the top story. First, we'll select the master node there, go to select, then click this, then go to assign load, and now you have to select this one, nodal displacement, and here you select the load pattern, sorry, pattern 2. This pattern 2 we have created for the pushover load application. So here again, it doesn't matter because we do not have any pre-existing load here. And here you decide the global degree of freedom. Now we are going to apply the load in x direction. So global degree of freedom will be 1. And here you specify the intensity, which was 300 mm for the top story. Then apply OK. Now here you can see whatever you have applied there, it has reflected here automatically. Similarly, you can apply the load for the immediate bottom story. Select the master node there. Then again you go to assign load, and here you select the nodal displacement and the pattern 2. Then now you have to enter 250. Then OK. Then let's come to the next story and go to assign load and 200. 150. So here you can see whatever loads we have applied, you can see all the applied load here, including the node number. This N38, 63, 88, these represent the node number where you have applied the load, and you can also see in which degrees of freedom that loads are applied. You can also double click on that. Now, if you want to change the intensity of any of these load parameters, then you can do it from here as well. Okay. So now we are completely ready with the model, and let us now go to the analysis step. We have to define the analysis step. So for that, we go to this option, then click on analysis step. And the approach what I have shown you earlier, let me open that once again. So we are going to first apply the gravity load, then we'll carry out the pushover analysis. And in the second, not second, there are two types of analysis. One is gravity followed by pushover, and another one is gravity followed by nonlinear time history analysis. Okay, so three steps will define, but we'll run two steps together, not all three. So first let us define the gravity analysis step. So we have just selected the gravity load application, whatever we have done, and here you decide what kind of analysis it is going to be. It is static, and now here constraint handler you can choose accordingly. Transformation handler is good, but since we are also going to follow this using the pushover analysis, so just to make the uniformity, I am going to apply penalty option here, and here it is written as load control pushover, although actually it is not pushover, uh, it is load control. Okay, so let it be as it is, and here it is load control only, and we do not have to change anything here. This is like entire load application is divided into 10 steps, and 1/10 of total load will be applied in each of those 10 steps. Okay, so instead of applying instantly, you are just splitting those into 10 uh, fractional intensities and complete it in 10 total steps. Here again, this is one of the best option to go for, and gravity load assessment will work fine with Newton solver. Then this also fine. Here you can reduce the tolerance little bit, and you would like to print some statements if want to track what is actually happening. So this step is now saved here. Now you can move it back to the left panel and proceed with the next step. So now this is the pushover analysis step. Here again we can either run the analysis in static mode or in transient mode, similar to how time history analysis are performed. But we'll go with the static mode because it will take less time. And here, as I said, we are going to use the penalty option. Now you can go for displacement quasi static way, and here you decide the time history what we have earlier decided for the push overload application, and it is asking how much step increment you want at past step. So when we defined the pushover load, um, in that we have used total 1000 steps and multiply it by 10 to make total 10,000 seconds. So we can use step size of 1. So maximum 10,000 steps will be performed. Here now you can change it to this because this is a little bit more stable compared to the Newton option, and in that case you would like to increase this little bit. The rest you can leave as it is. So again, take it back to the left panel and move this to the right one. And now this we are going to run in transient mode. Here you can go for HST, and now it is asking the duration. Earlier we have seen the duration was 19.99, and you can specify either zero point zero 0.01, which was the step size in the ground motion, or if you want you can make it even finer, like instead of zero point zero 0.01 you can go for 0.005 or something smaller than that. But I think for this ground motion, zero point zero 0.01 is a good step size. If it is not working, like you are facing the convergence failure somewhere, then you can come back here and reduce the step size later on. So these things again fine, you do not have to change. then okay. Now see, we have applied all the three time steps, sorry, analysis steps, but when running the analysis, you will not be running the pushover analysis and the time history analysis at the same time. Either you will perform pushover or you will perform the nonlinear time history analysis. Okay, both of these analysis will be preceded by the static gravity analysis. Okay, so what you can do is you can just uncheck whichever you do not want to run. Like in this case, I am uh, unchecking the nonlinear time history analysis and going for the pushover analysis. Once the pushover analysis is completed, then we'll come back to this and we'll check this one and uncheck the pushover load case. Okay. Then before going to the analysis, we'll also like to define some recorder parameters. It means what are the output parameters you want to record during this analysis. Okay, so we need at least the nodal displacement and nodal reaction, if not all others. So accordingly, let's define nodal displacement recorder. Here you can decide whether it is nodal parameters or element parameters, and whether you want for all nodes or at some specific nodes. Okay, so we want for all, and here you decide what kind of output parameter it is. Okay, so now we are going to define it for displacement, so let's keep it to displacement and then press OK. Similarly, you can also record the nodal reaction. Just change the name here, you can give any name, and same thing. And one more thing is, see here you can specify the degrees of freedom, whichever you want to record. Now for this one we are just going for the translational degrees of freedom, we are not recording the rotational degrees of freedom. Okay, and this is important for fiber section recording. Here you do not have to specify what you are going to record, just tick this one and all the fiber section like stress, strain, etc. will be recorded. Okay, if you do not want to record the fiber section parameter, then you can just uncheck this one. This is useful in case of if you have a large model where you have thousands of members and several thousands of nodes, let's say. There, if you do not need these fiber section results, just uncheck it, because including the fiber section parameters takes a lot of time during analysis, and also during the post processing. The loading, model loading will take a lot of time, that's why. But in this case, I would like to show you the results, some results from the fiber section, so I am just checking this also. Now here you can see whatever the recorder parameters we have defined, that reflecting here. So I guess now we are complete with the model and we can proceed with the analysis. So before that, let me save the model once again, and let me just have a quick review in case if I have missed anything. So I guess we are complete with the modeling part. Now let's start with the analysis. So we have to either you can press this button or you can also perform analysis from this, clicking on this perform analysis. So I find it easy to use this button instead of going to this menu option. Okay, so you can click on run analysis. Now the software is saying that it is not able to find the OpenSees executable by default. So what you have to do is just click on this and go to the directory where you have saved the OpenSees solver. So here I have kept it, and you have to select this one, OpenSys.exe, and okay. So OpenSys path is set to whatever directory you have selected. Okay. So now it is asking you to select a directory where it wants to save the TCL scripts, because after all, whatever modeling we have done is basically to write the TCL scripts which will be used by the OpenSys solver for performing the analysis. So if you want to use the scripts later on for any other purpose, like you want to verify the model, or you want to use it to uh, analyze your structure in any cloud-based analysis platform, HPC network. So there you can use the TCL scripts generated by the software. Okay, so the scripts are saved. Now it is performing the pushover analysis. It will take, here you can track the analysis completion, and I guess it will be done in 2 to 3 minutes. Let us wait. It's done. Now we can check the result. First, we'll see the story responses and the displacement and reaction files. Then we'll go to the visualization. So you have to go to this option, then display results. Now here you can see some options are like grayed out, which are not available for this analysis, and this bold written are showing that these results are available from this analysis. So first we'll check this one, nodal displacement. Just double click, and it is giving you the structured displacement parameters for all the nodes. So at the top you can track for which node and for which degrees of freedom. So for example, this one at node 1 displacement x, then node 1 displacement y, node 1 displacement z, then again it starts node 2 displacement x. Now if you could recall, when we defined the recorder definitions, there we have specified 3 degrees of freedom. So instead, if you have applied 6 degrees of freedom for each node, you would have 6 result parameters. Okay, now if you would like to download this as a CSV file, you can easily do it by saving it to a particular directory. So I already have some results saved from previous trials, so I'll just override those. Similarly, you can also check the nodal reactions and again save the results. See, now I am not explaining these things because this is a text file, so explaining the text file is difficult. I have to either plot this or I have to visually show you, otherwise it is difficult to understand from the text result. Now you can also check the fiber stress strain, and here all the fibers are um, available sequentially. You can click on this for each element and for each hinge. So if you could again recall, there we have specified 3 by 3 fibers for concrete sections. So total 9 concrete fibers will be there. Then in addition there will be 8 rebar fibers. Okay. So accordingly, here you have 9 plus 8 17 fibers for each end. So 17 into 2, total 34 fibers for both the ends at each member. So that's why you can see for element this is one member, then it is showing the fibers for both the ends. I means the first end, J means the second end, and it is also written whether it is rebar fiber or concrete fiber. In concrete also you can see whether it is cover concrete or core concrete. Okay, so you can just click on any of these fibers and corresponding stress strain results for that fiber is reflected here. Again, if you want to export these results in CSV, you can do it easily from here. So like this, you can select any fibers where you want to check the results. Okay. So this is what you can do from here. And here you can track the story response. Double click and Okay, so earlier what happened is at the end of the analysis, just before reaching 100%, the structure has reached like severe nonlinear range, and suddenly the displacement parameter was shoot up by several order. So that's why it was showing the this dot line shows the backbone, like the maximum how much has reached. So it was so large that actual values which was we have applied, for example, if you go to the displacement, we have applied just up to 180 mm. So earlier that was 300 mm, we tried with 300. So 300 mm was uh, highly negligible compared to several order higher value, which was just a numerical instability caused during the nonlinear behavior in the structure. So now what we did, we have reduced this load intensity so that we get the actual behavior. Now you can see this is how structure moves during. If you want, you can also play this animation, and you can increase the speed of that animation also here. Let me increase this. Okay, so this is how you can play around with this, and instead of displacement you can also check the story drift. Okay, so during pushover how the story drift varies. Now here one thing actually which is useful but so far we have not implemented is the actual pushover curve. Although that is implemented in another module, we have a life cycle cost assessment module. In that module we have already implemented that pushover plot, but in this conventional module that is not yet implemented, we'll be doing this soon, and probably by the coming month we'll release the beta point 2 version. There it will be available. So this is how you can track the results after analysis. Now we'll go to the visualization part also. We'll see some quick visualization, and after that we'll proceed with the time history analysis. So here you can set the parameter, displacement parameter which you want to track. Then if you want to select the fiber inch parameters, then you can do it here, and here which fiber you want to check, you can choose it from here. And also here you can select which resultant component you want to track. See, you might get confused between this and this. This is actually the degree of freedom in which you have applied your load. Now for this analysis we have applied the load in the x direction. That's why we will select x here, and this is the actual component which you want to track from this visualization. It means although you are applying the load along the x direction, it will also have impact on the y direction responses, on the z direction responses, and also the rotational responses. So that's why you can track all 6 degrees of freedom because of any particular analysis. So first we'll check because we have applied the load along x, so the major influence will be along the x only. Okay, so you can check this one, and you can again go to the animation and check how your structure behaves during the analysis. Okay, and here you can again control the speed of the animation, and instead of the solid view, if you want to check the fiber actual fibers, because we have used the fiber section for columns, so you can just uncheck this one and check this one. Now here you see in the sections you can see the fibers. If I zoom it here, for example, this, This is the fiber radius. You can reduce it to see a more clear view. Let me reduce it a little bit. Okay. So here you can see the beam, concrete as well as steel fibers. So this central fiber is the core concrete at the center. What you can do, you can click on any of this fiber and you will get this kind of tab. Here it specifies what kind of fiber is this and what is the ID of this. So element ID is 100265, location is hinge I, fiber core 11. So this is the first fiber in the core, and either you can track time versus stress or you can track strain versus stress, then get the plot. So it tells you that during the analysis this fiber behaved this way. Okay, so because this is concrete at the core, so usually it will not have that much damage. That's why it is showing only a linear variation, so it did not go to the nonlinear region of this restraint curve. So instead of core, let me pick a uh, concrete fiber from the edge. So this is cover, it is showing bottom 0. So this is also in the linear elastic zone. So this is one cover concrete fiber. Here you can see the concrete stress strain curve has traced through the entire, you can say almost entire stress strain curve. Okay, so like this you can see any fiber wherever you want to check how that fiber has performed during the nonlinear analysis. For example, I'll also go to one of the steel fiber, let's say from this, this is concrete, I guess this is steel. So here you see this is rebar 2 and this is the stress strain curve. Okay, so since this is uh, monotonic load application, pushover is actually monotonic. So instead of seeing a cyclic hysteresis behavior, you'll see a monotonic backbone curve only. So up to here it is linear elastic, then this is the plastic zone. So now at the end of the analysis, your So you can also track the like how each node behaves during the analysis in terms of displacement or forces, etc., with respect to time. Here, using this option, so it will be useful to track the control node where you have applied the loads. Now, for example, you want to see how this node 138 behave during the analysis. So what you can do, click on this and here you write 138 and it will show you the response of that particular node. Here it is written 138 and you see with respect to time and the displacement how it has changed. Okay. Similarly, you can check the results for any other uh, whether it is fiber or the node or any other things from these visual uh, features here. So now we'll go back and perform the nonlinear time history analysis, and after that, at the end of this, we'll also have little discussion on the TCL scripts. So go to analysis tab, then uncheck this one and check this time history load case. And before performing the time history load case, just here is the result data from the previous analysis. And now again hit the run button and write the TCL scripts. So now it is performing the time history analysis and let us wait for 2-3 minutes till it gets completed. So it's done again. You want to again check the results, you can go here. So I will not check the displacement and reaction this time. Just I'll show you the story response profile. So you can see how the structure behaves. This is actually the red dot line is showing the backbone curve. So you can track the maximum drift. In this case, it has reached up to a drift of 3%. This was actually the same drift level which we, not same, but in a similar range near to 3% in the earlier case. So this is how the structure responded during the entire time history. Now this 3%, if you compare with the codal provision, for example ASC 41, ASC 7, so I think they allow a drift of 2% or 2.5%. I didn't remember the values exactly. So this is performing better than that. And this is the displacement profile. It has gone up to a displacement of 300 mm. But when we have performed the pushover analysis, the structure was very much unstable to go beyond the displacement of 200 mm. But in case of time history analysis, you can see it has gone up to 300 mm without any problem. So this is what happens. You cannot decide the response based on pushover analysis all the time because pushover has a lot of limitations. So you have to, it is better to go for the time history analysis, and again, performing one time history analysis is not enough. As code says, you have to go for multiple time histories and take the average response. Okay. So again, you can go to the visualization and whatever result you want to track, you can track from there. So now I'll show you some of the sales scripts, what is recorded here. So let's open this first. Here you see the time series definitions. We have created three time series. First one is for the gravity load application. Then this is for the pushover load application. The pushover time history, 1,000 steps, whatever we have applied, it is written here. Then the ground motion time history, here it is written. Okay. Then you can see the element properties, the geometric transformation, two geometric transformation we have created, and then elastic beam properties, whatever we have applied to the beam members with the transformation tag of 2. Then if you scroll down, you will get beam width hinges. So this was used for column members, and here the transformation tag is 1. Okay. Then you also have the zero length element for the plastic ingredient in beam, and here you see the material ID for the degree of freedom 4 and 5. We have used the material ID 4, which was for IMK model, and for all other degrees of freedom we have used the material ID 3. Okay. The 3 was for the elastic material. So then you can check the material. We have concrete 02, then we have steel 02, sorry, then we have elastic material, and we have the modified IMK. And then you have this the output result, nodal displacement output. Now here you see OpenSys actually gives this as the output. You cannot read this from this text file. It's very difficult. So you have to convert it into a structured format like we have downloaded that CSV file, for example, this one. Okay. So here you get the node ID on top and the corresponding displacement parameters. So this is the exact same file, whatever is written here, nodal displacement. Only difference is in the CSV file, on top of each column, you have the node ID and which degree of freedom it is representing, and in a structure format so that it is understandable. But from this text file, it's not understandable. So if you are performing the analysis using the uh, command prompt from OpenSys as usually we do, then you'll get exact same kind of result output. So you have to do manual post processing, but in the software we have automated all these things, so you can read the result very nicely. Similarly, you have the nodal reaction output. Here also same thing, it's not structured, so again you have to convert it into structured format for understanding. Then this is the TCL script for node. So here you see the node IDs, and see up to this the node 175. These are the main nodes, whatever we have created at the beginning of the model creation. Then starting from this, all other nodes are the uh, zero length hinge nodes, like extra nodes created for connecting the elastic beam column element to the zero length element, and then again connecting the zero length element to the main node. Okay, so there you need these extra nodes which are not the main nodes. Okay, all the displacement or reaction, whatever you usually refer after the analysis, that will be referred corresponding to the main node, not these uh, imaginary or supplementary nodes. And in the same node file, we have also scripted the support condition. So fixed support condition for all these nodes, and mask definition is also written inside this, although the name is not means suggesting something else, but we have, instead of creating separate TCL script for each of these, we have just combined the things inside the same file. Okay, so here again you can see the mask components are assigned to the translational modes, sorry, translational degrees of freedom, and the rotational degrees of freedoms are not having any mask. So it depends on what kind of analysis you're performing and whether those rotational components are important to you or not. If they're not important, you can just switch off so that the analysis runs faster. Otherwise, the rotational component creates complexity. Analysis sometimes fails prematurely. Then this is the fiber section we have created, and here you see the um, geometry of these fibers, and these are the steel fibers. Okay, these are concrete fibers, and this is the analysis step where the solver logic has been scripted and all the fiber recorders. So the fiber recorders, what we have asked the software to record that, and this is the load application. We have like two kind of load, the live load at the floor level and the infill overloads, but OpenSys will not use those commands. It has its dedicated command for element loads. The same will be used. So by looking at this, you will not understand whether it is live load or some other loads because they will follow the same command. Okay. Then this is the main file which will be called during the analysis by the OpenSys. Okay, so here you can see we are calling all these individual script into a single file, and this main file will be called during the analysis. Now, instead of using the software for analysis, you wish to use these same scripts for cloud-based analysis, then you can use this. For example, you want to utilize the parallel computation facilities. So uh, those cloud platform definitely do not give you a platform for creating the model. So you can also use the software for creating the models and generating the script. So here we have another option for generating TCL. So instead of running the analysis, you can just click on this button. It will give you just the scripts and analysis will not perform. So you can also generate the scripts and do whatever you want with the scripts. So again, if you want to verify these scripts whether they will run if you perform the analysis in a conventional way or not, let me show you. Um, what I can do is, okay, so this I'll keep for the webinars because this video is going to be already getting so much lengthy. So we have an upcoming webinar on 24th May. There you can attend for more detailed discussion on the software and OpenSees based simulations, and we will compare the manual analysis using the command prompt and as well as using the software and see whether they give the same results or not. Okay. So I hope this introductory tutorial video on REOS software and OpenSys simulation will give you a very useful fundamental uh, to get started with the software when you get to use the software. Okay, so with that I would like to close the video and thank you very much for your attention and look forward to a lot of this kind of webinars, and I hope it will be useful to you all. Thank you.